So in last discussion we discussed about the plastic hinge modeling or lumped plastic hinge modeling of reinforced concrete beams. In this session we will focus on fiber modeling of columns and shear walls, right? So again I'll mention these references which you may refer for detailed discussions on the same topics. So now let's go to fiber modeling approach, this one, and we have discussed that already, that this is an approach where we defined the nonlinearity right at the material level. So we do not lump the nonlinearity at member level at the ends of a member just like we did in beams. Here we make material as nonlinear using their nonlinear stress strain curves, and whatever is the effect of that nonlinearity, it automatically manifests at the cross section level and member level. So if you define a nonlinear material first and then assign that nonlinear material to a cross section, that cross section can become nonlinear. And then when you assign that cross section to a member, when you draw that member, you are assigning it to a cross section, that member automatically become nonlinear. So no need of those lumped plastic hinges if you define the material as nonlinear, right? But you have to follow some certain steps to actually implement this approach in a particular software, for example ETABS. So I'll sweep through those steps also, 2 or 3 steps. How to define a nonlinear material, then how to assign that material to a cross section, and then how to tell the program that this nonlinear material should run throughout the length of the member, or it should run only up till a certain length of that member, because you may make the whole member as nonlinear or made of a nonlinear material, or you can only lump that nonlinear material up till certain lengths at the ends where you may expect the most inelastic action, because that may reduce your analysis time, that instead of using the whole element as nonlinear material, just lump that nonlinear material up till certain lengths at the ends only, but those lengths will be finite lengths, they will not be zero length, just like in case of lumped plastic hinge approach. Here there will be some physical length of the element which you will be defining, for which you will be using nonlinear materials, and then in between 2 of these segments you may assume the material to remain linear, right? So that will be actually lumped fiber approach. So fiber approach can be the distributed approach, actually it is distributed plasticity approach, but that can run along the whole length of the element or at certain segment which you may define. So the basic idea is, let me just quickly summarize that maybe here. Let's say that this is your cross section. Let's take for the case of column first. This is your column, you are viewing the side view of that column, and this is the column cross section, and then let's say it has few rebars, 4 rebars let's say, and they are running along the length of the column. Now the basic idea is that you divide this cross section into hypothetical you can say small elements which we call as fibers, right? Those are hypothetical small elements or small columns you can say, which are running along the length of that element. It can be beam or it can be column, and those fibers can be assigned with nonlinear stress strain curves, right? So this is a side view of that column. Let me draw the cross sectional view. Let's say this is the cross section of that same column. It has 4 rebars, 2 on one side, 2 on the other side. What I can do is that I can divide this cross section into some hypothetical, you can say, sub elements like this, right? So I cut that cross section into certain number of sub elements. Each of that sub element, let's say this one, this one which I am just shading, it is now running along the whole length of the column. Actually it may run along the whole length or up till a certain part of the length, we will decide that later, but it can run along the whole length of the element. Similarly, let's say this is one rebar, it is also running along the length of that element. So what we can do is that we can assign a stress strain curve to each of these fibers, right? So I can declare in the program that this is the stress strain curve which should be given to this sub element or this fiber, right? Now this is, I know that this is a concrete stress strain element, so this is my way of telling program that this is a concrete fiber, right? Similarly, to this circular shape area, I can declare this as another fiber and I can give it its own stress strain curve, which is steel stress strain curve with its own Fy and everything, elastic modulus. So this whole circular area, which will be the area of one rebar, that will be declared as one steel fiber or defined as one steel fiber with this stress strain curve, right? And similarly we can do it for all concrete fibers and all steel fibers. Ultimately, with this hypothetical cut which I just draw it here, so 1 2 3 4 5 and 1 2 3 4, so there are actually, it is a 5 by 4 mesh, right? So it's like 20 concrete fibers with 4 steel fibers, right? So with this cut I am actually saying that this cross section is made of 24 fibers. One is 20 fibers are concrete and 4 fibers are steel, right? And each fiber will be assigned with 3 things. One is the stress strain curve, which will actually tell the program that what material this fiber is made of. Second is the location of that fiber in that cross section. So that fiber will have a certain area. And third thing is that area property, right? So the location of fiber is actually the from the centroid of the area of that fiber up till the centroid of whole cross section, the distance between them in x and y, right? So let's say that this is the centroid of whole cross section, right? So I can define all those 24 fibers. I can actually define their areas because I know exactly how much is the size of that fiber, so I know its area, right? So some, let's say, inch square. Then secondly is the location of that fiber from the centroid of that small area up to the centroid of whole cross section. So the x distance and y distance from centroid, right? So actually 2 distance and 3 distance, because the centroidal axes are 2 and 3. So this is 3 axis, this is 2 axis of cross section. So the location of each fiber in 2 axis and in 3 axis. So once I give, let's say 2 axis is 3 inches, 3 axis is, let's say, 5 inches. So I know exactly where that fiber is located in the cross section. And third thing is the stress strain curve. So if I define these 3 properties in that cross section, what I have defined is called as fiber section, right? And that fiber section can run along the whole length of the element or up till certain distance from the ends, right? So just imagine now your cross section is just like a bundle of spaghettis. You have seen spaghetti bundle, that each line or each spaghetti is just one fiber, right? So your column is a bundle of spaghetti. Some spaghettis are made of concrete, some are made of steel, right? So for each longitudinal steel bar we have a spaghetti made of steel, right? And for each you can say concrete fiber, we have a spaghetti made of concrete, right? So it can be beam also, horizontal element divide into fibers, and column also, vertical element divide into fibers, and then it can be a shear wall section also. Shear wall leg along the cross section can be divided into fibers, right? So we may give one fiber for one steel bar or we may give two, you can say, rebars, we can lump them to make one steel fiber. In that case, the cross-section area of that fiber will be the sum of the cross-sectional areas of those two rebars, right? So one fiber will be representing two bars, right? Although obviously that fiber should be located at somewhere in the middle of those two rebars, but if we want, we can represent one steel bar with one steel fiber, right? This approach actually is implemented through plane section remain plane assumption. Actually, for example, imagine that you have a column which is composed of these fibers, hypothetically composed. So it's a bundle of spaghetti. Now that bundle is, let's say, subjected to bending. You can imagine that some of the extreme spaghetti will experience extreme tension. On the other side, they will experience extreme compression, but that can only happen if the ends of those spaghettis are restrained, right? If they are free to slide, then they will not develop any stresses, right? So this is an inherent assumption in this modeling approach, right? So this is implemented this way, that there is no slip between these fibers, right? So this is an inherent assumption. So no interaction between these fibers. They are hypothetical cuts. Actually it is all continuous material, but we have cut it hypothetically just for the purpose of monitoring the strains in each spaghetti, right? So once we give a stress strain curve to each spaghetti or each fiber, after the analysis we will be able to check all the spaghettis in that bundle, how many of them actually yielded or crossed Fc prime, or if they are steel, how many of them crossed Fy. So fiber by fiber we can check that particular column's performance. So we can even identify after the analysis that particular extreme fiber or extreme rebar yielded, but on the other side that rebar remained in the IO level or less than LS level, for example, right? The effect of shear reinforcement or confinement can be implicitly modeled in this approach. How? Because that confinement steel will improve the concrete stress strain model, stress strain curve. So that confinement effect can be accounted in the stress strain curve which you can give to your concrete fibers. With more confined steel, your stress strain curve, this one, given to your concrete fibers will be improved. Ultimately your column's behavior is improved, right? So just compare it now with that plastic hinge approach, where we were directly calculating or determining the member level response and giving it as an input. Here no need for that. Directly make a material as nonlinear. That nonlinear will ultimately result in a nonlinear moment rotation curve, right? Which we were previously taking from ASC 41 and giving it as an input, right? So actually the section designer in ETABS can plot the moment curvature curve and you can convert it into moment rotation curve. And how it is doing it? It is actually using fiber modeling approach without actually telling you. It is dividing your cross section into fibers of steel and concrete, and by default there is a nonlinear material given to each material in ETABS, right? Even when you define a linear material, there is an option for nonlinear parameters or nonlinear stress strain curve for that material, and there is by default some nonlinear stress strain curve given to that material already, right? So you may not use it for linear analysis, but that material already have a stress strain curve defined by default. So when you just draw a cross section and click on the moment rotation curve and it give you nonlinear curve, you should be surprised actually that how the program is able to tell that at this moment my beam will yield or column will yield, and at this moment it will be ultimate. It is actually performing nonlinear cross-sectional analysis using fiber modeling approach, and in that it is using that nonlinear stress strain curve which you don't know at start that they are already there in in the default, right? So for steel there is a bilinear kind of a model, Parkes model I think, and for concrete there is a Mander model or stress strain curve proposed by Mander. It is already there by default. So section designer use those stress strain curve, assign it to concrete and steel fibers, and perform nonlinear cross-sectional analysis to generate moment rotation curve for you or moment curvature curve for you, right? So this is exactly will be happening when you use fiber modeling approach at the structure level, that you define a nonlinear material, define this kind of a cross-section, fiber cross-section or fiber section for all of your columns, assign it to your columns and run the analysis. The program will be simply calculating the moment rotation curve for each of the element in the form of capacity, and then demand also can be simply imposed or checked on that capacity. But additionally, when you use that approach, you can even go to each fiber results also. Like I have given this particular fiber, I have given this let's say this stress strain curve I have defined in the program, and on that I will also define IO, LS and CP, because now our action deformation curve is no more moment rotation, it is stress strain. So the acceptance criteria will be in the form of material strains, right? How much material strain is my IO, how much material strain is my LS, and how much is my CP. So I will be defining a nonlinear stress strain curve for each material, and on that I will also be defining 3 markers, right? After the analysis I can come back to the results of same fiber and see that what is the demand produced by applied loading. Let's say I run a nonlinear dynamic analysis and I come back to the fiber result for the same column and for the same fiber, and I will be able to see such kind of a graph, that this line is my capacity line which I gave, and then this line, additional line which is imposed now on the same graph, is my demand line. This is the stress and corresponding strain produced by the applied loading, right? So just like I can compare the moment rotation curve, capacity and demand after the analysis in case of beams, here I can check directly at material level what will be the performance of that particular fiber, right? So resultingly I will be able to exactly identify which fiber of which column will go beyond the cracking level of my stress or ultimate FC prime, right? Now remember that this stress strain curve is coming from an experiment ideally, right? So each point on that stress strain curve should have a visual picture in your mind, how concrete looks like when it is here or it is here or it is here, right? So you have a picture of damage associated with each point on that curve, right? So when after the analysis you will come to know that applied loading have stressed that particular fiber up till this level, so you should be able to make a picture in your mind that that's how my column would look like after the earthquake, right? Similar is the case for any steel fiber. Let's say here was a steel bar, rebar, and I have given this stress strain curve to my rebar. After the analysis I come to know that my applied loading will stress my this particular rebar or this particular fiber up till this level, right? So I should exactly know that this bar will be yielded as a result of this applied loading. So you can even identify cracking, yielding, buckling, tensile yielding, compressive yielding, any material level failure can be identified or checked after the analysis. So this is one benefit of using this fiber modeling approach, that you can come back after the analysis and check fiber by fiber each element if you want. ASC 41 follows the chord modeling approach or moment rotation plastic hinge modeling approach, right? So it gives IOLS, CP and A, B, C modeling parameters and acceptance criteria in the form of plastic rotations. So ASC 41 is specific to a particular modeling approach, and that is not fiber modeling approach, right? So we have to decide our own IO, LS and CP, and we have to decide our modeling parameter, which is our stress strain curve, and that is easy to get from experiments. Material testing is our daily routine thing, right? But full member testing is not a daily routine thing, so therefore we require ASC 41. But for fiber modeling, we can test our steel rebar, we can test our concrete cylinder, generate this stress strain curves, and on those stress strain curves we can decide 3 performance levels, IO, LS and CP, if we are following the ASC 41 terminology. Or we can also define or give our own names, which is not possible in ETABS, by the way, to give our customized name to performance levels. It is possible in Perform 3D. So we can give it as tensile cracking, compressive crushing, or like that. So the names of performance level will be indicative of the actual material damage, right? But currently in ETABS it only fixes 3 performance levels, IO, LS, CP, in tension and in compression, right? So we have to use these 3 placeholders or 3 performance levels, right? So this was a quick introduction of fiber modeling approach. They are hypothetical fibers, they do not interact, there is no slip or friction or anything between them. They are just divided into fibers for the purpose of assigning individual stress strain curves, right? Now before moving forward, let me quickly explain another useful feature of fiber modeling approach. If you are modeling a composite section, right, this one, let's say this is your column, it has an embedded I section and some steel rebars also, right? This kind of a column, ASC 41 do not provide A, B, C, IO, LS, CP values for composite sections. You may have an irregular section. ASC 41 only provides modeling parameter and acceptance criteria for circular and rectangular column, but you may have a trapezoidal column or a triangular column or any other shape, right? Pentagonal column, for example. You may have a column with fiber reinforced sheets wrapped around it. You may have a column having a hole in it, right? For all those cases, your plastic hinge modeling approach, you will not be able to get those modeling parameters and acceptance criteria values for plastic hinge modeling of those columns. So you have to come to fiber modeling approach, because the beauty of this idea is, let's say that you have a steel section embedded. Now in that mesh which you will be actually making, you can directly assign those particular fibers the stress strain curve of structural steel, which are actually constituting that structural steel section, right? So let's say this is your section and this is your structural steel section, right? So in order to model that using fiber modeling, what you can do, you can divide this structural steel into small fibers, right? And then you can also make a cut, overall cut also. So whatever is the fiber which is made of structural steel, you give it a stress strain curve of steel, structural steel. Whatever is made of concrete, you give it to concrete, right? So you can handle any cross section. If there is a wrapping of fiber reinforced sheets, you can make a layer of small fibers which can be given a stress strain curve of FRP, and that's all, right? Let's say you have an opening in that, so you can make a whole fiber having the same area as that opening and assign it as a zero stress strain curve, or give it as zero null property. It will be modeled explicitly. So any material, a cross section made of any material, any shape or any irregular geometry, it can be handled using fiber modeling approach. You can always make a mesh, draw a mesh, and fiber by fiber give the stress strain curves, right? As long as you have the stress strain curve of your material you can model that as your column or part of your column. In case of column, since it can bend on both sides, it can undergo biaxial bending, so we cut the cross section exactly in this way, that we cut it in both directions like this, right, and then in this direction also, right. But for beams, since the primary bending direction is one direction, which is M3, right, if its cross sectional axes are denoted as 3 and 2, 2, if this is a column, it can have M2, M3 both, but if it is a beam, it can only have M3, right. So if it was beam, then only like fibers like these were enough, right. So no need to cut in vertical direction, because when it will be bending, only the fibers along the depth will be stressed, extreme tension, extreme compression. Each fiber can only develop axial force or axial stress in it, and therefore we give it an axial stress strain curve, right. So fiber cannot handle shear, it cannot handle moment, so it is not a standalone hypothetical element in itself. It is just a spaghetti which can only be stretched or compressed without buckling, depending upon which stress strain curve you give. So it will follow its stress strain curve in tension and compression, but that will be uniaxial, right. So fiber modeling can only handle axial flexural nonlinearity, right. It cannot handle shear nonlinearity. For that you require a shear hinge separately, right. Similarly, it cannot handle torsional nonlinearity, just like the moment M3 hinge in plastic hinge approach can only handle flexural nonlinearity of beams. Here it can handle the axial flexural nonlinearity of columns and shear walls. It cannot handle shear nonlinearity or torsional nonlinearity. For that you have to add another hinge element for that, right. So they can only have axial response. So fiber response is just one. How much is the axial force in compression or tension, and how much is the corresponding strain in that fiber, and after the analysis you will be interested in whether that strain have crossed IO level or LS level or CP level or not, right. Program have a systematic way of telling you that all of these columns have some fiber which crossed IO or some fiber which crossed LS or CP. So you can color code elements based on their fiber states, just like you can color code beams based on their plastic hinge states, right. So this is how a beam will look like when I cut it hypothetically into fibers. So this is a beam section. So no need to cut it in vertical direction, because the primary axis for bending will be, if this is that beam running, so this is how it is going to bend, right. So only fibers in this vertical, you can say, along the depth are enough. So all those you can say rebars at the top can be joined or lumped and can be represented by one hypothetical steel fiber. So the area of that steel fiber will be the sum of the areas of all those 4 rebars, let's say, and the location of that fiber will be exactly the level of those rebars. Similarly, the bottom steel can be lumped as one steel fiber, right. So this is the fiber section of that real beam, right, and along the length of that beam we can continue those fibers along the full length, or we can just lump them for a finite length on both sides. So these lines joined by these small circles, each of them is a symbol of one fiber, right. So from the side, when you look at this beam, you will be looking at fibers as they are laid along the length, right. So these are fibers, but they are not run along the full length, they are only located at some length L1, let's say, on one side and L2 on the other side, and in between them is the linear elastic frame element, right. So since our material can undergo nonlinearity, let's say, only at the two ends, So material can crush, yield or crack only at the ends. So we just lump it up till certain length. It can be, let's say 1d, where d is the depth of that beam, for example, or half d. So it is sometimes expressed as a multiple of the cross section size of that beam. And there is an extensive research on how much should be this plastic length, right? So ideally it is the plastic length LP, and different studies propose different plastic lengths. This is the length in which you can expect material failure under lateral loading, and different empirical expressions are proposed by different researchers as a function of cross sectional dimensions and as the function of the material properties like Fc prime and Fy. You can calculate this plastic length, or you can just decide based on some empirical or thumb rule. For columns, since it can bend on both sides, so you require fibers on both sides. So you cut not only in this direction, you also cut in this direction, right? And again, along the length you can run the fibers for a certain plastic length or along the full length of the element, right? For shear walls, you will divide the cross section in one direction only, because shear wall will not be designed to resist out of plane moments, so it can only resist in plane moments. So therefore you only require fiber in this particular direction. So you slice that leg of shear wall in this particular manner, right? So in this figure, this is the actual shear wall leg with actual steel, right? And then what they did is that for these 4 steel rebars, they just defined one steel fiber in the center, right? So this fiber which I just highlight, it is representing 4 steel rebars which are in this particular circle. Then the next 4 rebars can be lumped, or that can be represented by this steel fiber in the middle, right? So again this one, not 4, actually now 8 rebars are lumped here, and then again 4, and then again 4. So you should make sure that the area of combined area of all rebars should be same as the area of fiber, and then location of fiber should be the centroid of all those rebars which that fiber is representing, right? So ultimately whole of the rebars should be represented by some steel fibers, and whole of the concrete should be represented by some concrete fibers. So this was steel fiber, and then concrete fiber also you can make. This dot is showing the location of one concrete fiber, right? So in the middle where you have less confinement, you can have a larger area this fibers, and towards the end where you have confinement zones, you can have more fibers. So fibers can be closely spaced near the ends and can have a larger spacing relatively in the middle. So this shear wall is designed to resist only in plane loading, which means that if you're looking from top, if this is the, let's say, seismic load V, right, in this particular direction, so you can imagine how this bar will bend, this leg will bend. So side view will look like this, right? So now you have let's say, let me draw a bit of cross section also like this. Now you slice this, so these are all the fibers, right, like this. So this is how the shear wall leg will be sliced, right? So now you can imagine that with this applied loading, this particular fiber is going to undergo extreme compression, and this particular fiber is going to undergo extreme tension, right? So we have given their stress strain curves already. For concrete this, for steel this one, for concrete maybe this one, right? So each fiber have its own behavior which you have assigned it. So it will follow that behavior during the applied loading, and whatever is the stress produced by applied loading can be directly seen on its stress strain curve, and then its state can be seen after the analysis, right? Please note that these location of plastic hinges should always be coupled by the actual availability of that ductility in the members also, once you decide to include a particular plastic hinge in your nonlinear model, you should make sure as a designer that that particular location can develop the ductility which you are depicting in the form of your moment rotation curve, right? So you are giving a ductile moment rotation curve to your plastic hinge, and your real structure is unable to develop those plastic rotations, and it is having a brittle failure. Then this whole point of analysis is have an uncertainty or error. Then this whole analysis will be completely wrong, right? So please, that should always be coupled, that consideration. We should always be in mind that whenever you assign a ductile plastic hinge to any location, it is understood or well established that the real structure will be able to develop those plastic rotations. It is confined enough to have those kind of rotations and handle those kind of rotations, right? So the real behavior should be given as an input to the plastic hinges. So once you follow ASE 41, you should make sure that the ASE 41 curve, it should actually depict or exhibit by the real structure or at that particular location, right? This is another depiction. This is a real cross section. It is divided into some concrete fibers and some steel fibers, right? So you can have some, you can say you can lump few rebars to represent as one steel fiber. So the summary is that you need to have the exact location or detailing of your column sections before you start fiber modeling, right? For moment rotation curve for beams, moment hinge, you require only the top steel and bottom steel areas, and using that you can calculate the moment capacity. But for fiber section, you need the exact location of each rebar so that you can represent it using a steel fiber, right? So it means that logically the very first step of fiber modeling should be the definition of all stress strain curves for all materials, right? For all steel materials for different grades, you should first define a stress strain curve for steels. For all concrete materials which can be used in your column and shear walls, you should define a stress strain curve for those concrete materials. Next step should be actually the definition of fiber sections, and then last should be assigning those fiber sections to the members, right? So obviously you must have an information about material models before you actually start defining stress strain curves. So ETABS allow you to have user defined stress strain curves. This is that form. This is the form to define the stress strain curve for each material. So again, just like plastic hinge approach, this area is the actual force deformation behavior or stress strain behavior. You can go for user defined option, or you can use a predefined equation or model for stress strain curve, right? Mander model is the most widely used model, but you can define your user defined stress strain curve. These are the inputs required to define a Mander model or a simple parabolic model. This is an area where you define IOLS and CP, and they are in the form of material strains, right? So 3 levels in tension, 3 strain levels in compression, right? So you give your own numbers here. If this is how your stress strain curve look like, bilinear, you can call this yield point as IO. You can call, let's say, 2 times of the yield strain as LS, and let's say 5 times of the yield strain as CP, right? Now you know that my first IO level is actually the yield strain. After the analysis, you can ask the program to color code all those elements which crossed IO level. Actually you now know that those elements are yielded already, right? For LS you can say they are yielded but not heavily yielded, and CP level you can say they are significantly yielded far beyond the yield level, right? Similarly for concrete you can define 3 levels like this. This is the first point from where some damage start, then this can be LS, then when there is some degradation in strength you can call it CP, right? So you can call it as compression cracking start or onset of compression cracking, then you can say minor damage, and then you can say extensive damage, right? For tension side this will be your curve, so you can only have one, let's say IO, and LS and CP no need here, and IO simply means your tension cracking has occurred. In tension, concrete can have only one performance level, and that is cracking. Beyond that it's gone, right? Or you can also ignore the tension acceptance criteria, or you can give 0 values in the tension side, which means you are not interested in checking the tensile cracking, right? So you, after the analysis you will not be able to check that. So these 6 numbers are acceptance criteria. They do not affect your analysis results. They are just 3 markers in which you might be interested in after the analysis, right? So once you define nonlinear material, then you can start defining the PM2 M3 fiber hinge from the same list of available you can say plastic hinges which you used for lumped plasticity approach.